Okay, everyone. So just waiting for some more people to join, and then we'll get started. So while you're waiting to get started, you can certainly feel free to use the chat box if you know where it is. If not, I'll show you in a few seconds, and you can certainly just type in a hello, who you are, and maybe just a favorite VLAP memory or VLAP sampling memory since we're um, in the sampling refresher tonight. Okay, so in order to keep us on time tonight, I'm going to go ahead and start. Um, so welcome to joining us for the second session of part one of the 2021 VLAP workshop. Just a reminder, part two of the workshop, we'll start with the exotic aquatic species refresher on June 7th and end with the cyanobacteria refresher on June 14th. You can register for both of these events by going to the VLAP webpage. And again, while you're waiting and watching, you can certainly feel free to type anything into the chat box to the group. Just make sure that you address that to the entire audience and not as a question to staff. I am flying solo tonight, so if we have any technical difficulties, you might want to throw something in the chat so I see it, or just bear with me as we get through this. So also there's a handout in the handout section. If you joined us for the first part of this session, it's basically just an anniversary card for VLAP's 35th anniversary. So you could certainly look at that while we're waiting and before we get started. All right, so just a little bit of housekeeping. If you're not familiar with GoToWebinar, all attendees are muted and will stay muted. Your webcams are also not shared, so you can do whatever you want, just kick back and relax because we can't see you. This session is being recorded. It will be available to view at a later date. If you have any comments or questions, again, you can use the chat box here. So just type your message here, and then two, you can choose either the entire audience or as a question to the presenter. As I said, tonight I'm flying solo, so questions won't be answered as they come in, so I will try to address them at the end of each presentation. You'll also receive a follow-up email probably one day after this event. If you joined us for the first event, because there's two sessions in that event, you probably did not receive a follow-up email, but you will after this one. If you have any issues with your audio, there's this drop-down box here. So if your computer audio isn't working, you could certainly use your phone audio and call in. If that happens, make sure you enter your 4-digit PIN number, and you should have received a PIN number with your registration. And I think that's probably about it. So tonight we're going to do a brief lake ecology refresher, and then we'll move on to the lake and tributary sampling refresher. Okay, so let's see. As I transition here to the lake ecology refresher. All right. So let's start off with our lake ecology refresher. Um, so we'll start with just a brief overview of some basic lake ecology concepts. And so if you want a more in-depth explanation of lake ecology in New Hampshire, I do recommend going to New Hampshire Lakes article, video, and webinar library. They do have an excellent recording of their lake ecology webinar that you can view. So first, we'll talk about how lakes in New Hampshire were formed. As most of you probably know, our lakes were formed by the glacial retreat around 15,000 years ago. So as glaciers retreated and scoured the earth. Kettle lakes are very common, so they were formed when sediment from the retreating glacier buried large chunks of ice and really large chunks of ice. So these chunks of ice eventually melted. The soil above these chunks of ice caved in, leaving behind a depression, which eventually filled in with water. But that's not all. We also have lakes that were called oxbow lakes that were formed from sediment erosion and deposition from meandering rivers. So you see here, Horseshoe Pond in Concord is right here. This is the Merrimack River. And you can see another sort of horseshoe pond starting to form here. And then we also have lakes and ponds that were formed by both beavers and humans. So they may have created lakes or ponds by damming a river, which is what we call an impoundment. So here we have Moore's Reservoir Dam up in Littleton. So why is lake formation important? That's important because the way a lake was formed and its resulting morphology, and by morphology we mean the depth of the lake, the size, the surface area, as well as shoreline area, affects how a lake functions. So most lakes with deeper basins in New Hampshire have a unique seasonal pattern driven by temperature, both air and water temperature, wind, and currents. And these lakes are called Dimectic Lakes. So that brings us to our first poll of the evening to see how well you know your lake ecology, but also to see if you are just paying attention. So let's launch our first poll. All right, so the poll has been launched. So dimictic lakes have 2 mixing periods, and when do they mix? So we'll just give a couple more seconds to get people's votes in, and then we'll see how well we did. All right, so we're going to close our poll. So hurry up and get your votes in. A couple more seconds. Okay. So if you can see this, 86% of you were correct and guessed spring and fall. So let's see if I'm still sharing here. Okay, so moving on. So correct, spring and fall are lakes mix. So in the summer, lakes then stratify into different thermal layers based on water temperature and density. So we call this thermal stratification. In deeper lakes, this stratification creates 3 distinct thermal layers, which are called the epilimnion, the metalimnion, and the hypolimnion. So we're going to start with spring turnover and just a bit of information about spring turnover. So turnover occurs just after ice out, where water temperature and density is mostly uniform from top to bottom, and the wind and currents are able to completely mix the lake. So the water in the whole lake is mixing. And I'm going to start poll number 2. So let's see here. We're launching this poll. Alrighty. So poll number 2. Is warm or cold water more dense? All right, so we're going to close the poll. I will share it. Oh, here we go. Let's try that again. There we go. So 90% of you were correct. Cold water is more dense, and warmer water will float on top of that. So in the spring, as the days get longer, let's hide that. Okay. In the spring, as the days get longer, the sunlight will warm the surface waters, which creates a difference in water density. So the wind continues to mix this warmer surface water layer that's less dense, but it's not strong enough to mix the deeper, denser cold water layer. So this sets up the stage for summer thermal stratification. So as summer progresses, water temperature and density difference of the lake's layers become more noticeable. So relatively deep lakes, again, stratify into 3 thermal layers called the epilimnion, the metalimnion, and the hypolimnion. So the epilimnion is this warm upper layer. It's less dense, it's wind mixed, and that means it's usually well oxygenated. So we also see a lot of algal growth in this layer as it receives ample sunlight for photosynthesis. The metalimnion contains a thermocline where water temperature and density change rapidly with depth. So it separates the warmer oxygen-rich surface waters from the cold, sometimes oxygen-poor, deep water. If sunlight penetrates the metalimnion, we may see dense layers of algal growth here, where algae can utilize both sunlight and nutrients. The hypolimnion here is the cold bottom layer. It's more dense and isolated from wind mixing. Sunlight typically cannot penetrate, meaning there's no algae hanging out down here. The result is that the hypolimnion does not get reoxygenated during the summer. However, oxygen is continually being consumed by decomposers, and as the summer progresses, oxygen levels are typically depleted. In some lakes, oxygen levels are depleted to 0. When oxygen levels approach 0 in the hypolimnion, it can weaken the chemical bond between phosphorus and iron in the sediments, which then releases phosphorus into the hypolimnion, a process called internal loading. And this is an important process because phosphorus is the nutrient that feeds algal or cyanobacteria growth in a lake. So next, as we move from summer to fall, we see in the fall air temperatures start to cool and the days get shorter. So this starts cooling the surface waters of the epilimnion, making these waters more dense as they sink, and the thermocline deepens. So as surface and bottom waters near the same temperature and density, the wind can now mix them together and the lake turns over again. So remember in the previous slide I discussed how oxygen depletion in the hypolimnion could result in an internal load of phosphorus. So as you head into fall turnover, there's potentially an accumulation of phosphorus in the hypolimnetic waters that now gets mixed throughout the water column, becoming available for algae and cyanobacteria that were probably hanging out in the epilimnion and metalimnion. So this is why some lakes experience fall algal or cyanobacteria blooms. And then as we head from fall into winter, surface water eventually freezes and the water below the ice becomes nearly uniform in temperature and generally stays that way until ice melts in the spring. So now that we understand how the thermal structure of a lake works, let's talk about what other factors are at play in the overall health of the lake. And I'm just going to pause for 1 second while I help someone get audio. Try to. Okay, so for Nancy who's having trouble with audio, if you go to the audio drop down in your chat box and try your computer audio or your phone audio, if you try phone audio and enter a 4-digit PIN number that should have come with your registration, hopefully that will help you. Okay, so moving back on to a watershed. So there are a lot of factors that are in play in the overall health of the lake. So the first thing that we have to think about is a lake's watershed. And this brings us to our next poll. And let me see if I can launch that. To see if you all know what a watershed is. Okay, excellent. You are all paying attention. I'm going to close the poll. And I will share the poll with you. So you're all very smart. Yes, 100%. So a watershed is an area of land that channels all water to a water body. So whether it's rainfall, snow melt, creeks or streams, think of a watershed like the outside of a funnel where the lake is the bottom of that funnel. Okay. So lake quality can be affected by both the geology of the watershed as well as the land use activities occurring within it, such as development and agriculture. So what happens in the watershed is another important driver of nutrient or phosphorus loading to a lake, what we call the external phosphorus load. So much of this load enters our lakes and tributaries through stormwater runoff. As rainfall hits the ground or other surfaces, it will move over them, picking up pollutants as it goes and transporting those to the local waters. So larger watersheds tend to have more surface area over which precipitation and runoff can pick up the pollutants such as nutrients and transport them. So one thing to keep in mind when we're thinking about a watershed versus a lake is the lake size compared with the watershed size. So lakes that have large watershed areas compared with the lake area itself typically experience poorer water quality. So this is just a quick plot that demonstrates nutrient loading associated with watershed size relative to the lake's area. So you see as the ratio between watershed and lake area increases, we typically see an increase in nutrient loading. So this is important because a lake's morphometry determines how it responds to pollutant loading such as phosphorus. And by morphometry or morphology, we're talking about, again, the lake's depth, both the mean and the maximum depths. The lake size is determined by volume and area, and the shape or roundness of the lake. So these factors are important in determining a lake's retention time. So the retention time is the amount of time it takes for the full volume of lake water to be replaced. It's calculated by dividing the lake volume by the inflow to the lake. And it's also noted that it's the reciprocal of a lake's. So essentially, bigger and deeper lakes generally have longer retention times, meaning it's flushed out less often. This is important because the lake are retained for longer periods of time and also have more time to settle out to the lake bottom, thereby adding to that organic layer down at the bottom of the lake. And shallower lakes have shorter retention times and flush more often, which means pollutants flush out faster and have less time to settle. And so to sort of wrap up our ecology, so how a lake was formed, its watershed, its morphology, and the retention of nutrients and sediments in a lake impact the lake's trophic state. So lakes age naturally over time, meaning they gradually fill in with sediments, nutrients, and plants, a process called eutrophication. And this process can be accelerated by human activity within the watershed, such as development, erosion, fertilizer use, faulty septic systems, and agriculture. In New Hampshire, we classify lakes into 3 different trophic categories. Our oligotrophic lakes tend to have high dissolved oxygen levels, good water clarity, low nutrient levels, and less primary production or algal and plant growth, what we refer to as our young lakes in the aging process. Eutrophic lakes tend to have less oxygen, poor clarity, high nutrient levels, what we refer to as our old lakes. And then the mesotrophic lakes fall somewhere in the middle of those two, with moderate amount of nutrients, sufficient dissolved oxygen, and moderate primary productivity, what we call sort of our middle-aged lakes. So our next poll is pretty simple. It's just a yes or no, and let's launch that. So do you know the trophic classification of your lake? Okay, so I'm going to close the poll. The majority of you have voted, and it's, let's see, it's pretty much a 50-50. So a little bit more of you said yes, you know the trophic classification, but a lot of you also said no. So let's see if we can't help you out with that and see where you can find out that information. First, a little bit more information about trophic classification in regards to nutrients and chlorophyll. So in New Hampshire, the state has set thresholds for nutrient or phosphorus levels and algal or chlorophyll A growth for water bodies based on their best trophic classification. So ideally, we want to see phosphorus levels less than 8 micrograms per liter for oligotrophic lakes, less than 12 for mesotrophic lakes, and less than 28 for eutrophic lakes. For algal growth, we want to see chlorophyll levels less than 3.3 for oligotrophic lakes, less than 5 for mesotrophic lakes, and less than 11 for eutrophic lakes. And so if you don't know the trophic classification of your lake and you're interested in learning more about it, you can visit the NHDES Lake Information Mapper. Click on your lake and a pop-up box will appear where you can view the lake trophic survey reports for your lake. So that way you can see the historical trophic classifications. You also can find your VLAP reports there. Okay, so this is the end of the lake ecology session. So let's see if we have any questions specific to lake ecology. So there's a question about what are typical flushing rates for New Hampshire lakes, and that really, there is really no typical flushing rate. They vary greatly between lakes. And again, that's just basically the lake morphology and also has to do with the watershed. So how much flow is coming into the lake as well as the morphology of the lake. And then we have a question about why should there be more oxygen in an oligotrophic lake than a eutrophic lake? So again, oligotrophic lakes are what we call our young lakes. So they are younger sometimes in geologic time, as well as they have not been as likely influenced by any sort of human activity. So when you think about that, you typically think that they probably have less sediment that's accumulated on the bottom of the lake and less muck down there. And so again, that muck typically uses up oxygen, and because of all the decomposition going on down there. So if your oligotrophic lake has, less sedimentation that's come into it over time, it's typically higher in oxygen levels. And so we have a question about what about streams that feed a lake during the summer or other seasons? Would that water, new water, mix with any of the thermal layers? So yes, typically that water comes in, um, and it affects the epilimnion more so than it does the other layers. So initially, that would be, most of the time it's probably colder water, so it might come in and sink pretty quickly, or it might come in and get mixed in that epilimnion layer and warm up and stay there. So you have water that's mixing and currents that are also happening. So it could sink, some sinks probably, and some mixes. But mostly your epilimnion is affected by that surface runoff initially before the water sinks. Okay, so I think those are most of the questions that were answered for this. Unfortunately, there's someone still having issues with audio, but I just can't fix that right now. So I apologize, Nancy, and I hope that your audio has been fixed. So next, we're going to go on to our lake sampling refresher. All right. All righty. So moving on to our lake sampling refresher. So there are a couple of options on how to go about the lake sampling part of this refresher tonight. So either playing a new video that's located on the VLAP YouTube channel, or by talking through the slides. So I'm choosing to talk through the slides tonight, so just bear with me. Hopefully we don't have any, well, hopefully we don't lose you during this, because it might get a little boring. So I apologize for that, but we'll try. All right, so I encourage you to watch the newest sampling video that's on our YouTube channel. This actually is an on the water video, so it is this fourth video here. This fourth one here, VLAP lake sampling training video. So it can be accessed directly on this YouTube channel here, or you can go to the VLAP webpage and you can access it by clicking on the training link. Okay, so before you head out onto the water, consider watching the video, but you can also consult your field manual for a checklist of essential items that makes your sampling then go a little bit smoother. So we recommend sampling your deep spot once per month during the summer and between 10 a.m. and 2 p.m. during peak lake productivity. So if you choose to sample on the weekend, sample on a Sunday afternoon to allow for samples to be analyzed within the 24-hour hold time on Monday. So we need to analyze the samples within 24 hours. So for some of you, you may think that, delivering them at the 24-hour mark is okay, but we really would like them to be delivered within 22 hours of collection so that we can analyze them before the 24-hour hold expires. So you'll want to sample at the same deep spot location each month. The deep spot of your lake has been predetermined by DES biologists based on historical bathymetric mapping. So you can navigate to your deep spot and confirm its location either using a depth finder, a GPS unit if you have the coordinates, or you can also triangulate your location with 3 fixed points along the shoreline. So once you're at the deep spot, you'll want to anchor to prevent drifting. So if you do drift, just make sure that you try to reposition your boat to back to the original deep spot. Sometimes if it's a really windy day and you really just can't stay there, you might have to abort your mission, or you might want to try 2 anchors to help you stay at the deep spot. All right, so that's the end of our little reminders here. So we're going to go to part 1. So we talked about lake stratification. So if your lake stratifies into 3 layers, we're going to collect a sample from the middle of each one of those thermal layers. Thermal layers are determined by conducting a temperature profile. So stratified lakes have 3 layers. They're called the epilimnion, again, the metalimnion, and the hypolimnion. And unstratified lakes typically are shallower, and they have either 1 or 2 thermal layers. Samples are collected from the middle of each thermal layer for stratified lakes again, and for unstratified lakes, samples will be collected from the middle of the epilimnion. So the first thing you want to do when you want to collect your deep spot samples is consult your field data sheet to see what depths you sampled at the previous year. So DES biologists are typically going to write those depths in on your paperwork. So you're either going to sample at those same depths or you're going to conduct a temperature profile to determine the thermal layers and sample depths. So those instructions to conduct a temperature profile are located in your field manual. And if you'd like to do that, you can certainly borrow a dissolved oxygen and temperature meter from us. So there's a Klein finder. You could also borrow one of those. That's what a temperature profile looks like. So here the blue, get my pointer out, the blue temperature profile here. So this is the epilimnion, the thermocline, and the hypolimnion. And here are your instructions. Okay. So next, you're going to mark the depths you plan to sample at on your field data sheet. And then we're going to have you label your bottles. So at each depth, you're going to collect a large white and a small brown bottle. And this is called a set of samples. So next you're going to use the camera bottle, which is this bottle here. So first you're going to thread the chain through the top of the bottle here. So it's calibrated chain of rope. You're going to thread it through the rod in the middle. You're going to clip the chain on the bottom securely so we don't lose the bottle. And then you're going to check to make sure that it's clipped securely by holding just the chain where the bottle will hang from it. So once the bottle's set up, you're going to pull it apart so both ends lock into place. So that's called open. So when you pull the bottle apart, the ends will lock. You'll hear a click and you shouldn't be able to close them. So you're going to lower the camera bottle into the water column to the desired depth. The chain or rope has a mark every half of a meter. So you're going to place that mark on the water's surface. You're going to take the messenger, which is this little doodad here. It's the weight used to close the bottle. So you're going to attach it to the chain. We recommend attaching the messenger to the chain over the boat so you don't drop it into the water. And then you're just going to send the messenger down the chain to close the bottle. And this is what a closed bottle looks like underwater. All right, so once closed, you're going to pull the bottle up out of the water. When it reaches the surface, you're going to grab the camera bottle by the rod at the top to lift it out of the water, and then support the bottom of the bottle so it doesn't open up on you and you don't lose all the water. So this brings us to our first poll of this presentation. So let's see, let's launch this. Okay, so when you collect a sample using the camera bottle, what should you check for before filling sample bottles? Okay, so we're going to close the poll. We'll share that. All right, so the majority of you were correct. You're going to check for sediment in the sample. Okay, so here we go. Remember to check for any sediment. Um, if you observe sediment in the camera bottle, it means you either hit the bottom or you disturbed the bottom when you were anchoring, and there's still a lot of sediment that needs to settle out there. So either start over or sample at a slightly shallower depth, or just wait for the lake bottom sediment to settle out. Um, the reason why we don't want sediment in your sample is because it can affect nutrient levels and turbidity, leading to inaccurate results. So now that you have a clean sample, you're going to take your large white bottle and fill it with a small amount of water. You're going to rinse the bottle and discard the water. Then you're going to fill the white bottle up. Then you're going to pour from the white bottle into the small brown bottle. And, oh, hold on. Here's the next poll, which I'm sure you all know the answer to. So why don't you rinse the small brown bottle? All right, excellent job, everyone. We're going to close the poll. And so excellent. I'm glad that 92% of you answered this question correctly. So we don't rinse the bottle because it contains a small amount of acid as a preservative. So when you're filling this brown bottle, you're going to watch very carefully and only fill the bottle up to the shoulder. So once your brown bottle is filled, you're going to take your white bottle and then top it back off with water from the camera bottle before you dump this water. If you dump this water before you top off your white bottle, you will have to go back down and get another sample. Right, so you're going to repeat that process for each depth you're sampling at your deep spot. Then you're going to place your samples in a cooler on ice, or in this case, there was snow, so they pack that nicely with snow. All right, moving on to part 2, which is your chlorophyll A sample. So a helpful hint here is just to consult your field data sheets as you're sampling and your sampling checklist. But each one will walk you through what's next in the sampling process and the procedures that you should follow. So consulting your field data sheet, the next thing you'll see is that you're going to collect your chlorophyll A sample. And just to keep you entertained, here's our next poll. Oh, I didn't hide that. Sorry, you probably missed something. Here we go. So our next poll is promise I don't have too many more polls left, but we'll see. All right, so close that. And it comes as no surprise, or maybe, but I don't think so, that 100% of you were correct. That chlorophyll A is measuring how much algae is in the water. So chlorophyll is a pigment in algae that gives it its green color. So that's what we're measuring by measuring chlorophyll. So the starting depth for your chlorophyll A sample will be the mid-metalimnion for thermally stratified lakes. Or for unstratified lakes, you're going to go 2/3 of the total depth. So for this thermally stratified lake, here's the thermocline, and the middle of the thermocline is at 10 meters. And then for your unstratified lake, this is just 2/3 of the total depth, which is 2 meters. So if you conduct a temperature profile monthly, our staff will indicate on your field data sheet the depths previously sampled, so just follow that. So for your chlorophyll sample, you're going to fill a large brown bottle here. So note this bottle does not contain acid. So again, label your bottle with the starting depth of your chlorophyll A sample. So the starting depth, for example, if the mid-metalimnion is at 4 meters, you're going to label 4 meters on your bottle. So there are two methods that you can use to collect your chlorophyll A composite or chlorophyll A sample. The first method is your composite method. This is recommended for lakes where chlorophyll A sample is collected from a depth of 4 to 5 meters or less. So the composite method uses a camera bottle to collect the water from different depths and mixes that water in a bucket. So for example, if your starting depth is 4 meters, you'll want to collect a camera bottle of water from 4, 3, 2, and 1 meter, and then mix that water from all 4 depths in a bucket. So indicate on your field data sheet which method you're using and the depths your sample was collected at. So composite method and the depths. So make sure you use a clean bucket to composite your water into. So rinse your bucket with a little bit of lake water and just discard that. Again, you'll lower the camera bottle to the desired depth and close the bottle. Then you're going to pull that camera bottle out of the water and empty the water from the camera bottle into the bucket. So you're going to repeat that for each meter to the surface. So kind of looks like that. So make sure, the one thing to note here is that if you have a smaller bucket and you can't empty the whole camera bottle into the bucket for every depth, just make sure you use the same volume of water from each depth. So you're going to take your large brown bottle, you're going to rinse your large brown bottle with a little bit of water from the bucket and discard, and then you're going to fill your brown bottle from the bucket and put it in the cooler. So the next method is the integrated tube method. So just a note, if you're using this method, you're pretty much done with the camera bottle at the deep spot, so you can unclip the chain in the messenger and just put the camera bottle away at this point. So the integrated tube method collects a column of water from the surface to a desired depth at the same time. So it's similar to a big straw. So remember to mark the method again, mark the method and the sample depth on your data sheet. So we recommend the integrated tube method for any chlorophyll samples that need to go deeper than 4 or 5 meters. So again, remember to rinse your bucket, and then you're going to take the chain and the clip and clip it on the eye hook of the weighted end of your integrated tube. So that's this right here. So just note that the tube is marked every meter, as well as your chain is marked every half meter. So next, you're going to have one person lower the tube into the water, while another person lowers the chain into the water. And then you're going to lower both to the desired depth. So if your depth is 6 meters, you're going to put the 6 meter mark of the tube and the 6 meter mark of the chain on the water surface. Then you're going to crimp the top of the tube tightly, or close. If your tube has a valve, you're going to close the valve. So next you're going to pull the weighted end of the tube up by the chain. You're going to put the weighted end of the tube in the bucket, and then you're going to release the crimped end of the tube or open the valve. Then you're going to lift the end of the tube up, usually over your head, until all of the water empties into a bucket. Again, you're going to rinse and fill your brown bottle with water from the bucket and then put your bottle in a cooler. All right, and our last part of the deep spot sampling is your water clarity. So again, consult your field data sheet. So the next thing is water clarity or transparency. So you can consult your field manual as well for instructions. So transparency, it's really a subjective measurement. So it's affected by a lot of things in the water, such as algae or just the color of the water, so how tea-colored the water is. Any particulate matter that might be floating around. Maybe there's a lot of pollen, or it recently rained and there's a lot of silt or sediment that got washed into the water. It's also affected by wave conditions on the surface of the water, as well as sunlight. So we ask that you measure water clarity via two methods, so with and without a view scope. So first you're going to attach the chain to the eye hook on the Secchi disc using the clip. So next, on the shady side of the boat and without the view scope, you're going to lower the Secchi disc into the water. It's usually easiest to have one person watch the disc as it's lowered into the water and have another person using the chain to lower it. So lower the disc until you can't see it anymore. Then you're going to raise the disc slowly until you can just make out the white portion. Then you're going to mark the chain at the water's surface and determine the depth to the nearest tenth of a meter. Then you're going to record that information on your field data sheet. So we ask that you conduct at least 2 readings, ideally by 2 separate individuals, and then mark whether or not you saw the disc on the lake bottom. And then if you'd like to average that for us, just include the average of these 2 numbers here. So next, we ask that you move to the sunny side of the boat, and then you're going to repeat this process using the view scope. So you're going to put the end of the view scope in the water and make sure there are no air bubbles, or that the view scope really doesn't leak. And then again, you're going to repeat the process. So you're going to lower the disc into the water until you can't see it. And then you're going to slowly pull the disc up until you can just see the white parts. And you're going to mark the chain on the water surface and then estimate the reading to the nearest tenth of a meter. Again, record that information on your field data sheet and take an average. So that's it at the deep spot. So you will pack up your equipment. If you haven't sampled your tributary yet, we're going to move on to that next. Then let's see if there are any questions that we should answer now. There's a question of, can a pond be fed by a spring? So yes, springs are just groundwater inputs, and yes, that does occur in our lakes and ponds. Can you get a new field manual? Of course. So just request one. If you're coming to pick up sample bottles, we can just throw that in with the bottles. Uh-oh. And can someone tell me if you can see my screen or the poll? Hopefully you can see my screen at this point. But if someone could just type that into the chat, giving me a yes or a no, that would be great. Thank you. Okay. Moving on. Okay, great. Thank you all for letting me know that you can see my screen. Thank you very much. All right. So moving on to our tributary refresher. So this will go pretty quick and we should probably be done really close to 8 p.m. So thank you all for sticking with me here. All right, so again, you're going to consult your field manual for helpful reminders when conducting your tributary sampling. And we'll go over these really quickly next. So again, you're going to, like your deep spot, try to collect your samples at the same location each month. So consult your sampling station map. Here's an example here. So typically, you may have an easily identifiable landmark that you can use to remember where your sample location is, or maybe your sample location is a culvert, so that's also pretty easy to remember. If not, so maybe you just hike into the woods somewhere and it's not very noticeable or recognizable. It might be helpful to record the GPS coordinates of the location so you can navigate to that spot each month. So our next poll, so I hope that you're still with me and paying attention. It seems that most of you are, so that's excellent. Oh boy, this is multiple choice. This is fun. Here we go. Let's launch this. So the question is, when should you not take a tributary sample? All right, excellent. Wow, you guys are great tonight. Thank you for paying attention and being on top of things. So we're going to close the poll. And then I'll share that with you. All right, so 85% of you were correct, so all of the above. So we don't want to sample the tributary if it has standing or stagnant water that is not flowing. We also don't want to sample a tributary if the water is flowing, but it's just a trickle, as it's likely too shallow to obtain a sample that's free of sediment. So thank you all for participating in that one. Okay, so again, you really want to minimize sediment contamination in your sample. Again, the reason why you want to minimize this is that it can affect both the turbidity levels as well as nutrient levels or phosphorus levels in your sample. So if the stream bottom has been disturbed while you're accessing the site or trying to sample it, and you do have sufficient depth and flow to obtain a sample, just relocate either slightly upstream to obtain a sample that's free of sediment, or just wait for the sediment to settle out and flow downstream, and then you can just try again. So if the tributary station is hard to reach, we recommend using a sampling pole. You can make one yourself, or VLAP does have sampling poles that you can borrow. So our last poll of the evening, I believe, just to keep you entertained. And just curious how many of you actually use a sampling pool. I know that I have a lot of people that have made their own, and you are very inventive in how you make your sampling pools. Wow. All right, so I'm closing the poll. The majority of you do not use a sampling pool, so only about 20% of the participants are using a sampling pool, which is great if you need it. So that is good news. Okay, so moving on. We are done with our reminders, so let's just briefly go over how to sample a tributary. So that I know this is the easy part, or hopefully. So look at all these fancy slide animations, my goodness. All right, so again, you're going to want to collect a set of samples. So that's one large white and one small brown bottle. You're going to label your bottles with the lake name, tributary station name, the date, and the time the sample was collected. So you're going to rinse the large white bottle by scooping into the water flow. You're going to just cap the bottle, shake it, and discard the rinse water downstream from where you are sampling. So if you discard the rinse water upstream, you're likely to disturb the stream bottom and cause some sedimentation there. So you just want to avoid that. You're going to use the large white bottle to fill the small brown bottle. Remember, again, the small brown bottle does contain acid, so we don't rinse it. Then you're going to top your large white bottle off with additional water from the tributary. And it's as simple as that. But please remember to record the tributary name, flow conditions, and sample bottles that you filled on your field data sheet. So this actually really does help us out, not only in report writing at the end of the year, but as well as if we receive your samples, but maybe there's a bottle missing, we can consult this to make sure we know what you collected. So you're going to place your samples in a cooler on ice for transport to the laboratory, and then the dreaded E. coli. So now that we've covered the basics of the tributary sampling, we're just going to talk briefly about bacteria sampling in your tributaries, and specifically E. coli sampling. So we sample surface waters for E. coli because it's considered an indicator bacteria, meaning its presence could indicate the presence of other potentially harmful pathogens in the water. So we don't want E. coli in the water, nor do we want E. coli in our throat or cough drops. So what are some sources of E. coli to our streams? So some common sources are pet waste, so people don't pick up after their pets, agriculture, and that also includes just some of our backyard chicken coops. So chickens became really popular in recent years. So having your chickens, just remembering to properly dispose or cover your manure there. So if you do suspect any of these sources might be impacting your tributary or lake, it's definitely time to consider bacteria sampling. So first, you'll need to obtain a sterile bottle. And please note that we won't analyze a sample returned in a non-sterile bottle. So if the sterile tape is broken on the bottle, as you can see here, so this tape is broken, just don't use that bottle. So this could indicate the bottle has already been opened. And if that's the case, there could be cross-contamination, so it could yield inaccurate results. So a reminder, just don't touch the inside of the bottle or the cap with your fingers because our bodies contain bacteria on them. We also don't want to rinse this bottle prior to filling. And also you're going to collect your E. coli sample first if you're sampling your tributary or a lake um, before you collect your large white or small brown bottle. This is really to avoid any contamination from your hands or other body parts that might be in the water prior to collecting your bacteria sample. So again, review your field manual for proper sampling technique, and then once you're at your tributary sampling location, you'll remove the bottle cap, place the mouth of the bottle in the stream, and then you let the water flow into the bottle. Again, try to avoid collecting any sediment or organic matter in there. That could yield inaccurate results because a lot of our sediment contain bacteria in there. Then you're just going to twist the bottle cap tightly into place, put your samples in a cooler on ice. And one last reminder, our E. coli samples have a strict 24-hour hold time, and that is strictly enforced by our laboratory. So once you're all done with your samples, again, place them in a cooler on ice and return them to our laboratory within 22 hours so that they can be processed within that 24-hour hold time. All right, so that's it. That's the end of our refresher. So yay, you don't have to listen to me talk anymore. And if you do want to view the video, please, I encourage you to do that. Right now, there's just the lake sampling portion of that online. And then this summer, hopefully, we'll record the tributary sampling portion and get that up for you. So if you have any more questions, which I don't think we do, you can feel free to contact me with additional questions that you might have. And I thank you all for joining me tonight. And I look forward to starting the sampling season, so right around the corner. And have a happy Memorial Day weekend and enjoy. So thank you, everyone. Have a good night. Oh, one question may have come in. Oh, thank you. Oh, thanks, everyone. Have a good night.